Okay. It must be the thing's pressing against my screen. Anyway, we're on. Okay, great. So I was looking at our schedule. We only have 4 lectures left, which is crazy, right? Time flies. We have this week, next week, and then it's the exam. So in 4 lectures, we have to get through the rest of the icing model and Monte Carlo. Those are what we absolutely have to do, and then anything else is icing on the cake. So I'm gonna try to get icing on the cake. So I'm gonna try to. I didn't even intend that to be, but it just worked itself out. We're gonna try to get a Monte Carlo today, so that next week I can bring my computer in. Because what I like to do is bring my computer in and have the Jupyter notebook up and go through like the Jupyter notebook step by step, so you can really see how to write this code. Everyone said they've written Python a little bit. Yeah. Okay, then that's great. Then we have a big head start. So I don't have to write announcements, right? Homework's due in a week. Everyone knows that. Okay. Keep reading chapter 5 in Chandler. And so let's pick up where we left off and keep talking about the icing model, and then hopefully we can start Monte Carlo. John, can you check me over here at this time?
Yeah, you should be good right there.
Okay, great. So I know it's a Tuesday. So on Tuesday, what we have to do is we have to think back before the weekend. We have to think back to Thursday. What were we doing on Thursday? But you had these pretty pictures to remember. All of you remember these diagrams. They were burned into your memory, right? We were drawing these circles, and some of them had black lines, some of them had blue lines. And we argued that actually we can add them up fairly easily because all but 2 go away, right? And so that's where we left off. So we're continuing the 1D icing model. So this is another one. 1D icing model continued. Okay, and so we left off at, we got to an expression for the partition function, which looked like this. And this should be, I think, the last thing you have in your notes. You have Q equals, we still have to sum over all the states of the spins. S1 equals plus or minus 1, right? Which is whether the first spin is up or down. Same for spin 2. S2 equals plus or minus 1, dot, dot, dot. To the last spin, Sn equals plus or minus 1. And then the magic of these diagrams is they all went away except for 2, right? The one with all black lines and all blue lines were the ones that survived. The one with all black lines was the Cosh terms, and the one with all blue lines was the Sinh terms, right? So one diagram was Cosh beta j, and we have n lines, and each line multiplies one factor of Cosh beta j, so we get this to the n, right? That's all black lines, and then all blue lines was the other one. We have the hyperbolic sine, beta j to the n. And remember, it's what happened to spin factors here? Does anyone remember? Don't I carry around spin factors in my hyperbolic sine? They were squared, right? They were squared. And so these are plus or minus 1, and all my spins were squared. And so because they're squared, they're all 1, no matter what's in the sum. So that's why they go away. And so now what we do is we say, well, there's no spins in here, so this thing's just constant. I just move it outside the sum, right? So this can go all the way outside the sum because it doesn't depend on the spins. And so you get Q is this thing, hyperbolic cosine beta j to the n, hyperbolic sine beta j to the n, times all these sums. Sum S1 equals plus or minus 1, sum S2 equals plus or minus 1, dot, dot, dot. Sn equals plus or minus 1. And all I'm summing up is 1, because there's nothing left in my sum. And so what does this become? This product of sums? Anyone know?
So 2 to the n.
Yeah, 2 to the n, right? Because I'm summing up 1, each sum, I have 2 terms, I have n sums, so I get a factor of 2 for each sum, 2 times 2 times 2 times 2, 2 to the n. So q becomes this, q is 2 to the n times this factor. Okay, and you could leave it like this. This is perfectly fine. Generally, we make one more. This is closed form expression for q. So we've essentially solved the 1D Ising model exactly. We make one more simplification, and that's because in the thermodynamic limit, this goes away. Why is that? Let's see. Okay, so temperature is always positive. So note that for positive temperature, okay, hyperbolic cosine of something positive is always going to be bigger than hyperbolic sine of something positive. So for positive temperature, cosh beta j is positive and beta is positive. This is always greater than sine, hyperbolic sine, right? Because this is an exponential plus another exponential. This is exponential minus another exponential. Both those exponentials are positive. Okay, so this has to be greater than. We don't know how much greater it is. It could just be a little greater, but it's always greater. Everyone agree with that? If you think back to your Euler's formulas. So the point is, we don't care how much greater it is because we're raising it to the n, right? So for as n goes to infinity, the thermodynamic limit, even if this is just a little bit greater than this, when we raise it to the n, it becomes a lot greater than that, right? So as n goes to infinity, the hyperbolic cosine to the n is going to be much, much greater than the hyperbolic sine to the n. Okay? So this is just a simple, in the thermodynamic limit, this has to be true, and so we can drop this term. So we drop this term. So then we get in the thermal limit, we can just focus on the first term. We get q equals 2 to the n hyperbolic cosine beta j to the n. And that's your final closed form solution to the 1D Ising. Exact, okay? Exact solution. Okay, and this is the last time in class we'll ever see an exact solution. Well, no, that's not true. We'll see an exact solution in 2D, we just won't derive it. It's the last time we'll derive an exact solution in class. So appreciate it, right? So now think about all the things you've had exact solutions to in Stat Mech, right? Pretty much gases, monatomic, diatomic gases, phonons, and Ising model. Those are the things you can do. From here on, we need computer simulation or more advanced techniques. Okay, so this is the exact solution, and the whole point of doing the Ising model is to understand phase transitions. And so we solved for the partition function. Does that tell us anything about phase transitions? So what about phase transitions? So we want to know now, does the 1D Ising model predict phase transitions? That's why we're doing Ising in the first place. And you probably know the answer is no, because that's why we have to go to 2D. And the answer is no, but let's see why the answer is no. Okay? And so if you remember a week ago, we were talking about how do you define a phase transition in terms of the order, right? A first order, actually you guys tell me. How do we define a phase transition?
Wasn't first order based on?
The first order derivatives emerge, or second order, the second order derivatives.
Yeah, the derivatives of what? Free energy? Free energy. Yep. So no, that's exactly right. So you basically look at the free energy, and you take first derivatives of free energy. If those diverge, you call it a first order phase transition. If they don't, you go to second order. The second order derivatives. If those diverge, you call it second order phase transition. So that's the prescription we're going to do. So we're going to look at the derivatives of the free energy. So let's look at the first derivative of free energy. And so now you can kind of appreciate why we needed to solve for Q, because Q gives us the free energy, right? And so if we're going to take derivatives of free energy, we need to know Q. So that's why it's important to know Q. So the easiest one is to look at the energy, right? So we can look at the average energy is minus as d beta a d beta, right? D beta a d beta. That's a first derivative of the free energy. We can rewrite this in terms of the partition function. This is minus d log q d beta. Okay, so this is the first derivative of the free energy. We know what q is, so now we just have to take this derivative. Okay, so equals minus d beta. We have to take the log of this thing, right? So we get a log of q is n log 2 plus n log hyperbolic cosine. Okay. So when we take that derivative, of course this just vanishes. We have the derivative of a log of a hyperbolic cosine. May seem tricky, but just use your chain rule, right? And so the derivative of the log is 1 over the hyperbolic cosine, and the derivative of the hyperbolic cosine is hyperbolic sine. So we get hyperbolic sine over hyperbolic cosine, which is hyperbolic tangent. Right? So if you work it out, this term vanishes, and you just get, you're going to get a j from the derivative, so you're going to get a minus nj hyperbolic tangent. Okay, everyone see that? Let me do the second derivative before let's pause this. So what does the hyperbolic tangent look like? Actually, nowadays, many more people in the world know what the hyperbolic tangent looks like than, say, 10 years ago. Why is that?
Machine learning.
Yeah. So hyperbolic tangent is a common activation function in neural networks. So, people who didn't know what the hyperbolic tangent looked like before, if they use neural networks, now they know what hyperbolic tangent looks like. And so the hyperbolic tangent looks like this. We can plot, if we just look at hyperbolic tangent of x, it goes between 1 and negative 1. Right, so 1, here's minus 1, and it basically goes like, here's the asymptotes, and it goes like this. Inflection point. Okay? That's what it looks like. You use it for neural networks because it gives you a smooth, mapping between -1 and 1 bounds. It's a nice activation function. Anyway, that's a side point. But what we're looking for is we're looking to see if this is discontinuous or diverges. It's not, right? It's smooth. So we know we don't have a first order phase transition because the energy goes to the hyperbolic tangent. Hyperbolic tangent is smooth. Okay, so this is smooth. Smooth function. Okay. No discontinuity or divergence. Okay. So this is not a there's no first order phase transition in the 1D Ising model. Okay, that's what we learned by taking this derivative. Okay, so there's no first order phase transition. Let's go to second order. So the simplest second derivative is the heat capacity, right? The energy is the first derivative with respect to the temperature. Beta temperature, same thing, right? And so CV is dE dt, so CV is the second derivative of the free energy with respect to temperature, right? So second derivative of the free energy let's do the heat capacity. So the heat capacity is dE dt. And so we're taking another temperature derivative to get a second derivative of free energy. So we need equals, we just found out what the energy was, so it's the temperature derivative of this minus n j hyperbolic tangent beta j. Okay? What's the derivative of hyperbolic tangent? Just like, it's just, the hyperbolic derivatives are just like the trig derivatives, secant squared. Okay, so the derivative of this is secant squared. And the only trick is we need a d beta dt. So d beta dt is minus 1 over kt squared, or minus k beta squared. So we're going to get a minus times a minus. We're going to get n kb beta squared j. N kb beta squared. Oh, j squared, right? Because we have a j here, and we get another j when we take the derivative. J squared. And then the derivative of hyperbolic tangent is secant squared. Squared beta j. Okay, so that's the heat capacity, just taking the temperature derivative. And so now we need to look at what the hyperbolic secant looks like. And so if we plot the hyperbolic secant, hyperbolic secant of x versus x, it just looks kind of like this. It's smooth, kind of like this. Okay. The exact dependence doesn't matter. What we see is there's no discontinuity, there's no divergence. Right? And again, a smooth function. Okay, so no discontinuity, no divergence, and so there's no second order phase transition. Okay, so it's not a first order phase transition, it's not a second. In principle, I could just keep going. I could take more derivatives to look for a higher order. But at this point, I've learned something, hopefully. I've learned that the physics in this model isn't, the physics of the model just doesn't predict a phase transition, period. So there's something fundamental about the physics. So rather than taking more and more derivatives, let's just think about the physics and justify why there isn't a phase transition based on physical arguments. So, physical arguments for no phase transition in 1D. And it turns out it has to do with the dimensionality. Okay, so let's give some physical arguments. Okay, so I haven't told you about, what type of phase transition we expect, but if we're gonna have a phase transition, we better have two or more phases, right? If we don't have two or more phases, we're not going to have a phase transition, right? And so this is just, in this model, we just have a bunch of spins on a line. So what could possible phases be of spins on a line? How do we think about phases of spins on a line? Think about when we were talking about different phases of matter. Liquid crystals, a phase transition could be an ordered or disordered transition, right?
So could you go from like a region of all matching spins to a region of like mismatched spins?
Yeah, so basically if all my spins are up, that could be an ordered phase. In fact, the analogy there would be you have a magnet. You have an iron magnet and it's magnetized in one direction, right? Or they could be all down, that could be another phase. Or they could be random with zero magnetization. So really what I'm looking for is whether this thing can have all the spins aligned or all the spins have to be disordered, right? Because I could distinguish between those phases. If you measure the magnetization, you can distinguish between those phases of matter, right? So that's what we're looking. So in this case, a phase transition, so we need the existence, we must have the possibility for two or more stable phases. Okay? If we don't even have a possibility for two or more stable phases, there's no way we're going to have phase transition. And so here, these stable phases are going to be ordered, disordered, okay? Whether all the spins are aligned or they're all random. And we're going to characterize whether it's ordered, disordered by the magnetization of the system. Okay, so the question is, can a finite magnetization be stable? Okay, right? So if we're going to have a phase transition, well, one of those should be all the spins are aligned, and so we need to answer this question. Is this even stable for all the spins to be aligned? Turns out it's not. Okay. So let's consider two states to answer this question. So consider two states of our 1D Ising model. Okay. And the first state is going to be a perfectly ordered state. Okay, so state one, all my spins are going to be aligned. So draw all your spins aligned. They're all aligned. Okay, so this is spin 1, 2, 3, 4, 5, ... n. Those are all spins, they're all aligned. What is the energy of this state? If you think back to our Hamiltonian. Let me write it down. What was our Hamiltonian for the system? Do you remember? We don't have an external magnetic
Was it
field.
the individual spins plus like some coupling term or something?
Yeah, so if we had a magnetic field, we'd have an interaction with magnetic field. Here it's basically minus J is the coupling constant, sum over Ij prime, SI, where the prime indicates you're summing over nearest neighbors, right? But we rewrote that, didn't we rewrite that? We rewrote that to minus J, sum over I, SI plus 1. You remember that? Okay. So if they're all aligned, each term in the sum gives me what? SI times SI plus 1 is what? 1, right? And how many terms do I have in the sum? N. So my energy is minus N times J, right? So for this state, we have the energy is minus N times J. Okay. What's the magnetization of this state? We said the magnetization is defined by the sum over I mu times SI, right? Where mu is the magnetic moment of the spin. The sum, all these spins are up, so the sum gives me N. So the magnetization is N times mu, right? So magnetization M equals N times mu. Okay, great. Good. So that's the Moll line. Now let's think of a state where we slightly perturb, well, we kind of slightly perturb the system. We perturb the symmetry. What if we just create one unfavorable interaction? Okay. So what if we consider the state where all of these on the left are up, so these don't change. Okay. But now what I'm gonna do is, okay, suppose this is up, suppose this one is n over 2. Okay. And after this one, I put in one unfavorable interaction. So I put a downspin. Okay. What should the rest of my spins be to make sure I only have one unfavorable interaction? Should my next spins be up or down? Down, right? So I want to keep the rest of them down. Because they don't care whether they're up or down, because there's no magnetic field. They just care about what they are compared to their neighbor, right? And so, yeah, so I was going to get to that. So Kevin's correct. We are thinking about periodic boundaries, right? So essentially I have two unfavorable interactions. I have an unfavorable interaction here, okay? And I have an unfavorable interaction at my boundary, here and here. Okay, so I have two unfavorable interactions here. Two unfavorable interactions. Okay, so why did I pick this state? Well, first of all, let's think about the easy. Now I want to write the energy and the magnetization of this state. What's the easy one? The magnetization. Notice I made n over 2 up. It doesn't look like that in my drawing, but n over 2 of them are up and n over 2 of them are down, so my magnetization is 0, right? 0. So that's a big difference. Right, here I have a non-zero magnetization, the maximum magnetization I can have, and here it's just 0. Right, so these are very different systems in terms of, if you did an experiment, you get a very different answer because the magnetization is very different. What's the energy of this one? So the way to think about the energy is it's almost this, except this interaction is now unfavorable, and this interaction is now unfavorable. So you have to add 4. So it turns out it's minus n plus 4 times j. Because it goes from a plus to a minus, right? So when you go from, it goes from a minus to a plus. So the minus to a plus gives you a factor of 2, right? So this gives you a factor of 2. This interaction gives you 2j on top of this, and this interaction gives you 2j on top of this, and so that's why you have a 4. Does that make sense? Yeah?
So if you had a row of all up arrows of
That's right.
spins, except one of them flipped,
Yeah.
you would still only have 2 unfavorable interactions.
Yeah, that would have the same energy as that, but that doesn't have magnetization equals 0.
Okay.
So the reason I chose this is because I want magnetization equals 0, and you'll see why.
Okay.
Yeah, that's right. So here's my question. If we're going to have a phase transition, we need to have a stable phase, right? This phase needs to be stable, right? based on these numbers, is it possible that this phase is stable compared to single spin flips that ruin my magnetization? So the answer is no. Okay, so basically, and we'll see why. So let me just write it down and we'll see why. So the small change in energy, right? One thing to notice is the energy difference here has no end dependence. It's not extensive. So as n goes to infinity, minus nj and minus n plus 4j are very, very similar, right? The 4 is negligible as n goes to infinity, right? So this gives you a hint that there's almost no energy difference between this, right? One interaction and an infinite number of interactions isn't going to do anything. So the small change in energy between states 1 and 2, right, is insufficient to stabilize the ordered state. Is insufficient to stabilize the ordered state with magnetization M equals N U. Okay? And essentially there are just not enough interactions, right? Basically I need to, in order for this to be stable, I would need a higher energy penalty to do this. So we would need more interactions, right? We would need more interactions. More interactions would give us a bigger energy penalty to do this, right? Bigger energy penalty. So how do we get more interactions? Well, we either have a different Hamiltonian or we go to a different dimension. If we went to 2D, right, then I'd have 4 neighbors around me instead of just 1. Right? So 2D has a bigger penalty for doing this. 3D has an even bigger penalty. And so if we go to higher dimensions, we get something different. 2D, 3D. Okay. So let me just go through this a little more, just so you can see why this is true. I'm saying the small change in energy is insufficient to stabilize this state over this. Okay. So let's just calculate it. So let's calculate the probability of having this energy magnetization versus the probability of having this energy magnetization. Okay. So remember, what's our formula for the probability of a system having a specific energy in the canonical ensemble? We've done this a lot, right?
Sum over I, EI, PI.
No, for PI specifically.
Yeah, no, that's right, which simplifies into P of E, the degeneracy, right? We take the degeneracy of E times the Boltzmann factor over Q, right? That's always the probability to have a specific energy. It's what you said, John, but the sum gives you the degeneracy, right? So we've seen this before. And so let's write this down for these two states, okay? And what I'm going to say is this one's a lot more probable. The probability to have an energy which looks like that is a lot higher than this, okay? So let's write it down. So if we write it down for this, the energy is minus nj, right? So the probability of minus nj. What's the degeneracy for this state?
2.
1.
Oh, for
Right.
spin up, I guess.
For spin up,
Yeah.
right? I only have one state with spin up. Right, so there's only one way they all can be spin up. So this is 1. Degeneracy is 1. So we have 1. E to the minus beta e. E is minus nj, so I'm just going to write e to the beta nj over q. Okay. Now let's see the probability for having this energy. P of this is minus n plus 4j. Okay. What's the degeneracy here? A little tricky. I was thinking about this before class. Little tricky. Suppose you had one break. Forget your periodic boundary conditions. Suppose you had one break. Then there would be n places in your chain where you could draw that break.
Would there be n minus 1 spots? Because it's the spots between each.
So I want to say there's n over 2. That's what I want to say the degeneracy is. Because if you have one break, then there's n places you can make that break. But now what we're doing is we're making a break, and n over 2 later, we're making another break across the periodic boundary. Right? And so that means your n breaks would be double counted by a factor of 2 because we've already made the other break. N over 2 spins over. It doesn't really matter. The point is that it's proportional to n. The only thing that matters is proportional to n. I want to call it n over 2. People agree with that logic?
Wouldn't you also have a state where the first ones are down and the second ones are up? Wouldn't be n over 2
Yeah, but
two?
yes, but if we could call it the same state because we'd have translational symmetry. Well, I see what you mean. Yeah, no, that's a good point. So then we could call it n, right? So basically we'd have n over 2 because of my argument, and then Kevin's argument is, well, these could be down, these could be up. So then we'd have a factor of 2 there. So we call it n. So the only thing that matters is proportional to n, but I like n. So let's call it n. So let's say the degeneracy is n. Okay. The energy, we know what that is. So it's e to the beta, e to the minus beta, minus n plus 4 j, okay, over q. Okay. Now what we're going to do is let's factor the minus beta 4j out of here and group it with this term, right? So we can write this equals n e to the minus beta 4j, I can pull that out, e to the minus beta 4j. And the rest of it is e to the minus beta minus nj, which is just this. So I'm running out of room, sorry. E to the beta nj over q. Okay? So the point here is that there's only one thing that's different. Right? This. Yeah? Right, see that? Because this is the same as this. So that means the ratio, if you say, what is the relative probability I have a system that looks like this, with this energy, this magnetization, compared to a system that looks like this, it's this factor. Right? Everyone agree with that? And that means that I don't care what beta and j are. And the limit n goes to infinity, this is always going to be infinitely more probable than this. Right? So this is just back of the envelope calculation, considering two possible states in the Ising model, but just from this sort of back of the envelope rationalization, you get the point that it's impossible for this state to have any finite probability. Yeah? And that's why there's no phase transition, because this state is just not stable. It's not stable to have finite magnetization. It's highly improbable because of this logic. Everyone kind of get that? It's an important argument. Yeah?
So by increasing the number of interactions we can have between spins,
It'll change this.
you'll change that.
Basically, this thing needs to go as n or something, some power of n. We need an n dependence here to compete with that n. So let's go to 2D and I'll illustrate what I mean. Okay? So let's go to 2D. So what do we? Let's make the same argument in 2D. Motivate why we think we should have a phase transition. We'll give exact results from Onsanger, show that there is a phase transition, and then we're going to talk about how we're actually going to do it, because we're not going to do what Onsanger did, right? So let's go to 2D. Okay. So here's why we expect there's going to be a phase transition in 2D, because we're going to form if we make the same argument where we take this system all aligned and then we form this interface, the interface is fundamentally different in 2D. Okay? So we expect a phase transition. And what I mean is we expect a stable ordered phase. Okay. In other words, we expect to have a stable stable phase with net magnetization. Okay. But the absolute value of magnetization is greater than 0, anything but 0, right? Because the energy of an interface grows as n to the 1/2. Okay. So let me draw a picture and then you'll see what I mean. So now let's consider the state with 0 magnetization. That's the analog of this thing in 2D. Okay, so the analog here would be all spins are up on my top row. Then all spins are up. Okay. And then at some point I break and I start drawing rows where all spins are down and all spins are down. Okay, so here's my 2D lattice. Okay, and so this is the analog of that system I wrote over here. And right here is where I'm breaking my spins, right? And so this state has magnetization 0, okay? But the energy difference, just like over here, we said, what is the energy difference between all spins aligned and going to this? Here I had to pay a cost of 4J. To do this. what cost am I going to have to pay here? I'm going to have to pay cost for each spin in the row, right? And how many spins do I have in the row? Well, if there's n spins total, then I have n to the 1/2 spins in the row, right? So I have n to the 1/2 spins in my row, right? And so my energy cost now goes as delta E, where I'm writing delta E is just the energy difference for taking them all aligned and breaking them at this row. It goes as 2 n to the 1/2. Okay? And so the key point here is the argument I made in 1D no longer holds. Because you could go through the exact same analysis with these probabilities, but now your energy cost depends on n. Right? And so as n goes to infinity, you don't really know what's going to happen. Right? You have a degeneracy that's favoring breaking the spins, but you have an energy cost which goes as n, which is favoring it staying ordered. So you can't make the same argument. Right? So it's a different, completely different story than 1D. Okay? I can't prove that there's going to be a stable phase. I can't prove there's going to be a phase transition. All I can tell you is it's going to be different, and we can't make the same argument. Right? Everyone agree with that? And so in order to know what's going to happen, we either have to look at Ensonger's results or write our code. There's nothing else I can say. I can say that there's a possibility that we're going to have a stable phase. Okay?
So why did we say that stable phase has to have magnetization larger than 0?
We're saying that essentially, if you think of the phase as something you can observe experimentally, something you can, a phase transition is between two phases of matter that you can do an experiment and say this is different than this. And here the only thing we can probe is the magnetization. And so if the magnetization is different, we could do an experiment which says you're different than you. Right? And so if we're gonna have a phase transition, we have to have something which has non-zero magnetization if we're gonna say it's different than my completely disordered
Okay, so
state.
you're saying the other.
Yeah, good question.
So for the state you've drawn out though, then all of the spins cancel out, so we got 0 magnetization.
Yeah, exactly.
All.
So this state has
Oh, of course. that's
magnetization equals 0. I'm saying, can I make the same argument as here that's saying this is, in 1D I said this is always much, much, much more favorable than this because of this argument. And I'm saying I just can't make that argument anymore. So I don't know. We have to do it a different way. Yeah. So it's an open question whether all up will be stable. But you'll solve that on your computer, don't worry. In a couple weeks, you'll have a beautiful code you can run on your laptop, and within about 10 seconds, you'll be able to answer that question. Right? That's the amazing power of computer simulation. Okay, so what we're gonna do, 10 seconds after your code's written, and you hit go. A 20 by 20 icing model, running like 100,000 steps is more than sufficient, and that should take less than 10 seconds on your laptop. Okay, so what are we going to do? We are going to give the exact result, which is going to be our goal. Okay, so we're gonna transition into Monte Carlo, right? For how we're going to do this. So we are going to solve the 2D with Monte Carlo. We can't do it analytically, like we did for 1D. And so I'm going to have to teach you Monte Carlo, which we're going to do in the next couple lectures. But before I teach you Monte Carlo, I want to give us goals. Right? And our goals are going to be the exact results which we have from Ensonger. And those are going to be our goals that we want to reproduce with our computer simulations. Okay, so our goals are to reproduce Onsonger's exact results. Okay? So what I'm going to do is I'm going to write down Onsonger's exact results, and I'm going to tell you what we're going to do, tell you what our goal is for the computer simulations. And so if you want to read this paper, you know, if you don't believe me that this is just an incredibly hard proof, you should just look at this paper, right? So you can look up this paper. Onsonger's original paper was Phys Rev, volume 65. This was in 1944, okay? 1944. 32 pages, right? 117 to 149. 32 pages of just mathematical physics, nothing else. No words, basically, just two questions. Okay, it's what it takes to prove this. So you can look at the paper just to get a feel for, you know, why we're doing an Ising model. If you read this paper, or you look in Chandler, you see these exact results. And so we're going to have exact result for partition function. The exact partition function is this. This isn't going to be one of our goals. Our goal is to calculate magnetization, but I'm just going to write it down so you have it. Q, for a 2D Ising model, it depends on the temperature. There's no external field. Function with no external field. No external field. Okay, so there's no external field. It only depends on the temperature and number of spins. Okay. And it looks like this. At first it doesn't look too bad. It actually looks, oh, where was my Q for 1D? Sorry, I erased it. Someone tell me what Q is for 1D in the notes. 2 to the n, hyperbolic cosine beta j to the n, right? Okay, so it looks almost like that, except we're hiding, we have a 2 hyperbolic cosine beta j e to the I to the n. That's it. So it looks exactly like the 1D, except for that factor, yeah? Okay, so you say, oh, that's not too bad until you learn what I is. All right, I is not imaginary I. I is this integral with I is this integral 1 over 2 pi. I'm just gonna write it down, something nasty. Integral 0 to pi, some dummy variable phi, integrator of phi, log 1/2 1 plus 1 minus kappa squared sine squared phi to the, I need a 1/2, my 1/2 is right here. So this equation is in Chandler, so you can check me against Chandler, but this is right. Okay, and that's not all. And this kappa is also something nasty, kind of. Kappa is 2 hyperbolic sine 2 beta j over hyperbolic cosine squared of 2 beta j. Okay, that's what Q is. That's your 2D Ising model. And that equation is in Chandler, so you can double check this. The next equation I'm going to write down isn't in Chandler. And so make sure you copy my next equation, because if you don't copy my next equation, you're going to have to dig for it in here, which is not going to be fun. So that's Q. We're actually not as interested in Q as we are in the magnetization, okay? What we're really interested in is the net magnetization. So our primary goal in the Monte Carlo is going to be to reproduce this equation in this graph. So our primary goal with Monte Carlo, okay, and I'm just going to abbreviate Monte Carlo MC, is to predict magnetization as a function of temperature. Okay, that's going to be our primary goal. And so this next line I write down is really important because this is going to be the analytic result that we're going to try to reproduce. Okay, so the analytic result for magnetization, and again, write this down because you're gonna need this for your. This is going to be your target. What you're going to do is you're going to graph this. You're going to do your computer simulation, and you're going to compare what you get in the computer simulation against this analytic result. So this you're going to graph. So let me carefully write it down. It's this. So the average magnetization of your Ising model. Capital M is the magnetization of your Ising model. This means the average. We're going to normalize by the number of spins, right? Because if we have 20 by 20 spins, you know, this is extensive. If we have 100 by 100 spins, I can't give an extensive number. So we're going to normalize by N, right? Equals average of little m, right? So this is the magnetization, this is the average magnetization per spin. Average magnetization per spin is what we want to calculate. And the result is this, and this is, I double checked this equation. This is correct. 1 minus hyperbolic sine of 2 beta j. The hyperbolic sine is raised to the minus 4. So that's why I have another parentheses. Okay? So I have a minus 4 for the hyperbolic sine. And then everything in brackets, the 1 minus this, is raised to the 1/8. Okay. That's what the magnetization is if we are low enough temperatures. Okay. So this is true for some temperature lower than the critical temperature. I'm going to say for beta greater than beta C. Okay, so beta is inverse temperature. So temperature lower than critical temperature is the same as saying beta greater than beta C. And it's equal to 0 for beta less than beta C. Okay? So that's what it is. I'm going to draw it on a graph. And there's one other thing about this formula. Here it said the magnetization depends on the magnetic moment mu. There's no mu here. I'm assuming a unit magnetic moment. Okay, so this assumes mu equals 1. I'm just defining the magnetic moment to be unity. Unit magnetic. And there's no loss of generality there, right? I'm just defining a unit system. I can always define a unit system. And here I'm just defining a unit system where mu equals 1 is the definition of my unit system. Okay. And so if there's a unit magnetic moment, then the average magnetization is just the average value of a spin. Okay? So any questions before we plot this? This is really important. This is going to be our goal.
This is the spontaneous magnetization, right?
Yeah, well, so we'll see. There's no field here. So this is a result with no external field. And so I'm gonna circle this in blue because I really want you guys to. This is the key thing we're gonna focus on. Okay. Yeah, so let's talk about spontaneous magnetization. Let's plot this thing and then we'll talk about it. Okay, so let's plot it. What does it look like? Let me plot it over here, I guess. So let's plot average M, okay? It depends on beta J, okay? So this is sometimes a little tricky for people to understand, right? It's like whenever you are working with a physical problem, right? What doesn't matter, the total energy never matters. What matters is the energy relative to the temperature, right? Because you always have a factor of beta E in your partition function, right? And so basically, you know, you can, as long as you scale the temperature and you scale the energy by the same amount, the physics is all the same, right? And so that leads to properties in thermodynamics where you have laws of corresponding states, essentially. And so the point is that this depends on beta J, only the product of these. Basically, the energy constant over the temperature dictates the physics. And so we can just plot this versus that product beta J, okay? And so in your code, essentially, you can choose one of these to be 1, and you can just change the other one since the physics only depends on the product. We'll talk about that more. So, if I plot this, okay, what's the maximum value it can be? Well, 1, because if the average magnetization is the average value of SI, you know, the max this can be is 1. So 1 is going to be my maximum. So we're going to have 1 up here. This is the average M on the y-axis. 1 is my asymptote. If all my spins are aligned, then average little m is 1. Okay. And so this is going to be average m equals 0 down here. Okay. Let's see, where's point 9 is going to be a nice point to draw. So here's point 9. What point should I draw on my x-axis? It turns out that yeah, beta J is here, right? The key point is where beta Cj is. That's where I expect the physics to change. And so, what is beta C? Okay. Okay. Beta C is a value where this thing goes to 0. Okay. Right? At beta C times J, this thing goes to 0. If this thing's going to go to 0, my hyperbolic sine must go to 1, right? So at beta Cj, the hyperbolic sine of 2 beta Cj must equal 1 in order for average m to equal 0. Okay, so that's the key point. The definition of beta C is where this goes to 0, it goes to 0 and this equals 1. You can graph this or plug this in, and it turns out the value of beta C where this equals 1 is about 0.4407. So beta Cj equals 0.4407. Okay? So that's my magic value on this plot where I hit 0. So I need to draw that. So let's draw that point. Let's draw it right here. Okay? And so this value right here is beta j equals 0.4407. Okay, and let's let me draw some more points. Let me space it by about 0.05. So let's say this is 0.5. This is 0.55. This is 0.6. So what it looks like is when beta is less than beta C, this is 0. So this left region, beta is less than beta C, so this is 0 right here. The magnetization is 0 for that region. Then once you hit beta C, which is like this, it starts to behave like this. You can graph this. What it looks like is a sharply rising function. Let me just put a reference value. Around 0.5, it's at about 0.9. So we have a point that's right around here. Okay? And so we know, and at 0.6, it's about 0.97. So this is about 0.97. This is about 0.9. Okay? So it rises really fast. It's going to go like this. And asymptote out. So that's what it looks like. Okay? And so John's right that above this value of beta, we have spontaneous magnetization. All of this is spontaneous magnetization. Okay? So, right? Note that large beta is low temperature. That's a little confusing, right? So as I'm going, so let me just write that on the graph. Right, so this is lower temperature, right? And this over here is higher temperature. Right? That's important to realize, right? Temperature is inverse with beta. So low temperature is over here, high temperature is over here. As you go to low temperature, your system becomes more and more ordered until you get a low enough temperature, all the spins are up, right? And that's what you expect. You expect to see some ordering at low temperature, just like a crystal. So this agrees with your intuition, and then you get a high enough temperature, and things just disappear at the critical. At the critical, there's no longer an ordered phase anymore. And this is spontaneous. There's no applied field. So there's nothing telling the spins they need to order besides interactions with themselves. John, you look like you have a question.
So we have looks like a smooth function. 1 minus sine or sinh whatever of 2 beta j.
This is a smooth function, right?
Yes. But so what happens like locally right around beta cj that makes it jump where it looks almost I don't know, it looks like a cusp or a something that's not continuous, right?
Yeah, it's because of these powers, right? It's because essentially as this thing approaches 1, this approaches 0 really fast, right? Because you're taking all these powers. You're taking essentially, this becomes, you're taking a -4th here and a 1/8 here. So you're taking a lot of roots of this thing, right? So if you take a root of something, it gets closer and closer to 1. You know what I mean? And so that means that this, as this approaches 1, this approaches 0 really fast, which is why it drops so much. I mean, that's mathematically how you would think about it. Physically, it's because that, well, remember a week ago, we drew that, remember that free energy curve we drew?
With the,
Yeah, with the two minima and the hump. You guys remember that? And we said that the definition of having two stable phases is if you have two minima and a hump, right? And we said, what do we say about the critical temperature? It goes flat, right? But you don't, your minima basically wash out and your hump washes out, so that there's no distinction between phases, and your system just fluctuates all over the place. And so that's what's happening here, near the critical point. So basically, we could do this with a computer simulation. We could compute the free energy of the ordered and disordered phases, and you would see, right, if you had basically, well, let's do this later. Let me do it later. I'll do it more rigorously later. But you would see two minima. Over here, you'd see two minima, and as you go to the critical point, they wash out and it becomes really flat. And so that means you have fluctuations. Over here, you have fluctuations between all spins up, and then they go to all down, and then go to all, and then go to all down, and there just be random fluctuations. And you'll see that in a computer simulation. It'll look really cool. Right? So your computer simulation, when you run your Ising model, it's going to look boring. It's going to look boring over here. It's going to look boring over here. But you're still going to be able to compute this curve, right? So what you're going to do is you're going to change these values. You're going to compute this, and you're going to plot it, right? So your Ising model, you're going to do this. You're going to draw this plot, and then your Ising, you're going to run your Ising model at different values of beta j. And obviously, you know, you don't want to wait. You could run beta j equals 20, but that would waste your time. So you're going to run different values of beta j in the interesting regions, which are around 0.5. And you're going to run it here. You're going to compute the average magnetization. And you could run 10,000 Monte Carlo steps. You could run 100,000, you could run a million. Those of you who are patient, you know, okay, suppose Pablo's really patient. All right, so Pablo is going to run, I'm almost out of time, so I might as well just have some fun, right? Pablo's going to run 1 million Monte Carlo steps, right? Who's impatient? Who wants to be impatient? Kevin, you want to be impatient? Kevin's going to be impatient, right? And Kevin's going to run, say, 1,000 Monte Carlo steps, right? And so, I'm using the same color. Let's say Kevin's data is circles and Pablo's X's, right? And so Pablo's data is going to look really good. Pablo's going to get this, 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 this. Pablo's going to be almost on the curve. Over here, this is going to be really hard to reproduce. So you're going to be able to reproduce this pretty well. You're going to be able to reproduce this pretty well. And then as you get to the critical point, your data is going to be a bit scattered. It's going to be like that. Okay? Just because critical point, you have a lot of fluctuation, so it's hard to sample. So this is going to be a pretty good result, right? If you have an Ising, if you get this from your Ising model, that's pretty good, because then you've pretty much traced out the curve, right? And Kevin's going to be, his sampling is not going to be as good, so he's probably going to be fine over here, right? And then maybe he's starting to get some deviation, some bigger deviations than Pablo, because he's not using enough sampling. Right? Something like that. Okay, and then maybe that's Kevin's data. And so that's what you guys are going to do, essentially. And you know, you can run your code as long as you want, but the goal is we're going to trace out this curve approximately, and you're going to get agreement with Onsanger, and more importantly, you're going to be able to visualize this thing, what it looks like. Okay, great. Well, that was almost perfect timing, because I'm out of time. But we've gotten to the part where we've motivated our goals. And so Thursday, we're going to jump into Monte Carlo. And this is the most important thing to keep in mind. If you want to forget this, you can forget this. I'm never going to test you on this formula, right? But this is really important. I don't know why Chandler doesn't have this formula in his book. It took me a while to dig through this and find that formula. It would be much more helpful if Chandler actually put that formula in his book.
You know.
When was Chandler written?
Ooh, long time ago.
Long time ago? We thought like 60s?
No. I mean, Chandler, right? He probably started his career in the mid 70s, early 70s.
Okay.
He'd probably get his PhD in the mid 60s. He got his PhD with Peter Woolness, I think. So I think he wrote his book in the 80s, and it was revised maybe. See you guys.